This is a list of collaborators that contributed to these projects. And I want to start with the description of equipartition analysis. We heard a lot about that on Tuesday. So equipartition analysis is the idea that we see a radio synchrotron source, and we're trying to infer the properties of the emitting region. And the basic problem here is that we have at most 4 observables: the frequency associated with the minimum Lorentz factor electrons, the self-absorption frequency, the peak luminosity, and perhaps the time since the launch of the blast wave. But we're trying to infer at least 5 parameters. So we are missing observables to actually fully solve the system. And the trick that is used here in order to make progress is to notice the following fact, that if you look at the total energy, in the sense that it's the sum of the energy in electrons and the magnetic field, then for fixed values of the observed parameters, this energy is very strongly dependent on the radius. And there is a typical radius, which is called the equipartition radius, where you get a minimum in the energy. If you deviate even slightly in either direction, you get a huge increase in the energy. So this is quite lucky. It means that you know that the radius cannot be too far away from the equipartition radius. However, it comes at a price, and the price is that for the exact same reason, you cannot say that the energy is well constrained by this analysis. Even if you deviate a tiny bit from the equipartition radius, the energy can shoot up by orders of magnitude. So this has to be taken as a sort of caution that when we do equipartition analysis, very useful, but cannot be used to infer the energy. Now, another thing that I want to point out here is that you can do this for either the relativistic or for the Newtonian case. This is all done on axis. I will go to off axis in a moment. You can get this typical equipartition velocity that you can estimate from the observables, and I will show you why this is important in a second. So then the extension to the off-axis case is what Tatsuya and Zvi have done in their work, and this adds another free parameter, basically the viewing angle relative to the emitting material. Generally speaking, you now have this bigger parameter space for given observations that you're trying to infer. If you go to higher Lorentz factor and if you go to lower theta, that tends to decrease the energy. So that's good if you're trying to minimize energy. However, for a fixed set of observed parameters, you see that you can get these double minima in the energy as a function of radius, meaning that there is a solution which has a radius much greater than the equipartition radius in this geometry. So not only the energy is not well estimated by this equipartition analysis, but also the radius can be quite far away from the equipartition radius if we allow for this kind of geometry. Okay, moving on. So how does it work in practice? This is a nice case of 1644, and you see here many snapshots. In each snapshot, there is a spectrum. Fitting for the spectrum gives us an idea about these spectral parameters, and then connecting the dots as a function of time gives us the evolution of all these properties with time. Now, you can see how this works for this specific case of 1644 here in terms of some of the observed or inferred parameters, this beta equipartition, equipartition radius, and equipartition energy. And here the on-axis analysis is what you see as the dots connected with a black solid line. And one of the things that people realized right away with this event was that it looks very strange in the sense that when you do this equipartition analysis on axis, you see an energy that is increasing over hundreds of days. This is something that is not naturally expected if you just have a blast wave that is evolving without energy injection. And so indeed, this was the suggestion that you might have energy injection in this case. What I will suggest here is that there's another way to interpret this, which has to do with simply viewing the jet mildly off axis. In this case, as time goes by, you are seeing closer and closer to the core of the jet, where there is more energy that is becoming available to the observer within the beaming cone towards the line of sight. And therefore, you naturally get an increase in energy without having to actually inject energy over a long time period. In terms of the equipartition picture, so this is now with both the on and off axis analysis, and you can see that roughly what we would want to do is to move from this branch to that branch in this kind of schematic way. I will describe it in a bit more detail later. But staying for a moment with this idea of equipartition and when and where exactly we need to question it. So another thing that we have to account for is the evolution of the frequencies with time. And one relatively clean example to look at is the evolution of nu m with time. So nu m with time has to evolve at least as fast as this. In fact, at late times, it will only be much faster, t to the minus 2 after the jet break, even faster than that in the Newtonian case. And as long as the outflow is relativistic, it does not depend on the external density profile. So why is this interesting? Because for this event, 1644, for over thousands of days, the evolution of nu m is consistent with something like t to the minus 1. And even if you account for energy injection in the first few hundred days, that still doesn't allow you to get this over thousands days time scale. And that shows you that there is an inconsistency between what is inferred from the equipartition model, even allowing for extra degrees of freedom in terms of energy injection, and in terms of what you would expect from actual dynamics for the evolution of nu m. So equipartition gives you a solution at any given time, but there's no guarantee that the connection in time between those solutions is self-consistent with dynamics. And that's a key element that we have to keep in mind. So maybe one more point about this is equipartition is very good. People should certainly keep doing it, and I'm not trying to dissuade people from using it, but we have to use it as a way to pinpoint cases of interest. We cannot then take the results of equipartition and just apply them as is to infer the physics. So the thing that I want to suggest instead is to do forward modeling. And the idea here is basically an idea that has been used for many years in the GRB literature. So you have a blast wave, it's running into an external medium. You get a forward shock running into the external medium, a reverse shock running into the blast wave. Over longer periods of time, what you care about is really the forward shock. And then this forward shock accelerates electrons, it enhances magnetic field, and you get synchrotron and synchrotron self-Compton emission. This, as I said, works very well in the GRB context, and it's straightforward to apply it also to the case of TDEs. So we understand the dynamics, we understand the conditions in the emitting region, given those equipartition parameters, if you like, of how much energy goes towards magnetic fields and electrons. And then if we add this extra ingredient of the viewing angle relative to the jet or the outflow, we can describe the emission. And here there's another kind of useful trick, and it is the fact that if you want to know the flux that will be seen by an off-axis observer at some time and at some frequency, you can use the flux that would have been seen by an observer along the axis of the jet at a slightly earlier time and at a slightly higher frequency, and then using the ratio of the Doppler factors between the off and on-axis observers, you get this nice closed relation between the off-axis flux and the on-axis flux, and you see that the exact dependence here depends on the geometry, how far you are away from the jet, and how highly beamed is the core of the jet. So in any case, this is something that allows us to do these calculations very quickly, and we can scan over a large parameter space and search if we get results that are consistent with a given set of observations. So we did this for 1644, and indeed we, even with this relatively simple-minded, I will call it, model of a top hat jet that is viewed mildly off axis, we can get a decent fit to the observations in different bands. You see here all these vertical lines at various places. These denote either dynamical times of interest or times where two frequencies in the synchrotron spectrum meet or cross through the observed band. So you see that it can create quite a complex light curve at any particular band that you're looking at. And this, again, is the type of thing that, if you don't do forward modeling, would be very difficult to infer. There are other constraints we can use here, such as the radius constraints that we have on the size of the system, and we need to have enough energy to power the X-rays early on. But if we take this model, then it allows us to potentially learn some very interesting things about the outflow. We can constrain the opening angle of the jet, which is something that is otherwise quite difficult to do. We can constrain the energetics, and these, of course, will be very relevant for the rates of those events and their potential uses as sources of ultra-high energy cosmic rays, which I will talk on towards the end of the talk. As you increase the viewing angle, what happens is that these light curves get steeper and steeper in the rising part, and you get faster and faster rises towards the peak. And you might want to ask, how fast can it actually go? So let's start with the on-axis case. If you're observing a jet on-axis, more or less the best you can do is observe at a frequency that is below the peak. In this case, the peak could be going towards you, the peak flux could be going up, and this maximizes the rise of the flux as a function of time in your observed band. The best you can do is basically 2 to the third. If you have a declining external density profile, it actually is slightly flatter than that. So this is kind of an absolute best case scenario for the on-axis case. However, if you're off-axis, the situation is different. So imagine, again, this on-axis flux has some spectral dependence, temporal dependence, and now you want to calculate what it looks like in terms of the off-axis flux. So you can use the same formula that I showed you before, converting the Doppler factors from the off to on-axis emission, and you get essentially this relation for the temporal index of the off-axis flux relative to the temporal and spectral indices of the on-axis flux. And just to give you one example, in the same frequency band that we were looking at before, and for geometry where the jet is post-jet break and viewed from a far angle, then you get these extremely fast rises in the off-axis flux. If you take a uniform medium, it could be as fast as t to the 10. This is, of course, very idealized, and it assumes a completely top-hat structure for the jet. But even if we relax this a bit, and even if we take k that is, let's say, density going as r to the -1, you can still get these very fast rises in the off-axis emission. So as Asaf already mentioned, this is something that we applied to 18HYZ. Maybe one more comment here before I move to 18HYZ is that if you want to do it for a general regime in terms of viewing angle, in terms of power law segment in the synchrotron spectrum, we have all of that in the paper, and you can get exactly this closure relation between spectral index and temporal index for the off-axis case. So these are things that can help us tell if this is what's going on in a given event. And you can see that they match well, these asymptotic power laws match well with actual light curves that we get from numerical integration until the point where you get very close to the peak, and then you have some curvature that cannot be ignored. Okay, so this is now the case of 18HYZ that Asaf was showing before, and indeed we can fit it with such a model. You need to have a very narrow jet. It needs to have a huge amount of energy, but this is what is needed for this interpretation to work. In fact, there's a lot of degeneracy in the allowed parameter space for solutions here, because most of the frequencies that we observe are in the best fits that we have more or less within the same, or almost all the data is within the same power law segment of the synchrotron. So there's actually a large degree of degeneracy in terms of the parameters. This is a quick plot about that, which I will not get into too much due to lack of time. But going back to Asaf's comment before, if we see that it keeps rising and the peak has not yet been obtained, in principle, that's still possible. We had a lot of still degenerate parameter space with the observations we had at the time that we published this work. Okay, so moving on in terms of what else can we get from these off-axis outflows. So we mentioned that the jets that we've been assuming so far are more or less top hat, but you can also take structured jets. These are things that we are doing in the context of gamma ray bursts. And when you have a structured jet that is viewed off-axis, so here in these plots, the observer is at the center of the circle, the jet is at this white cross, and as a function of time, you see the flux centroid maps, and they're moving closer and closer towards the jet. Basically, you're always dominated by a region that is up to 1/gamma away in terms of angle from the line of sight towards the core of the jet. And understanding how this angle that dominates the emission changes as a function of time allows us to calculate the light curves. I won't go into this again because there's not enough time, but depending on a critical parameter, theta star, you can get double-peaked light curve or single-peaked light curves. This is slightly less relevant to the TDE case compared to the GRB case because the Lorentz factor in TDEs is probably lower. But this is what you need. You need gamma times the opening angle of the jet to be large for these kinds of double-peaked light curves to show up. And we know how to describe all of these segments analytically. So there are things here that we can test with data. We can also look at the evolution of spectral frequencies with time. So these two will be different for an off-axis situation compared to an on-axis situation, and they're different between structured jets and far off-axis top hat jets. Structured jets, typically you get very flat evolution. It basically, you get the same time dependence as you get in an on-axis jet viewed pre-deceleration. And I leave it at that unless you ask me for more details. For off-axis jets, you get things that are very steep in terms of the evolution. Same analysis as we did for the flux can be applied here, and this is the result for nu-m. Another test that can be used is polarization. Off-axis jets tend to be a lot more polarized than on-axis jets. If you assume that the magnetic field is tangled within the plane of the shock, this is more or less what you get. You see here on the top for an off-axis jet, and these things for quasi-isotropic or isotropic outflows where you get essentially zero polarization. And again, this can be described rather well, even analytically. So we have a good handle on that. So kind of generalizing, what can we do if we want to now test for a given radio event, if it's coming from an off-axis jet or delayed ejection or something else. So we have the best thing that we can do, which would be to test for superluminal motion of the flux centroid. That also in the GRB case was the smoking gun. That I think here would be the smoking gun too. But we also have supporting evidence that we can use, and I mentioned a lot of these things already: size, these closure relations between spectrum and light curve, evolution of the frequencies, and polarization. And crucially, off-axis jets at some level should be there. So if there are jets, there surely are also off-axis jets. They cannot be avoided. And measuring the opening angle of these jets will be very important if we want to know what is the rate of TDE jets compared to TDEs in general. In the last minute I have, I'll just briefly mention ultra-high energy cosmic rays. So it turns out that these jetted outflows, relativistic outflows, satisfy the conditions in order to accelerate very high energy particles, high enough to reach basically the highest energies that we see in the ultra-high energy cosmic ray spectrum. These jets can reach those conditions after a few hundred days. So they are a potential source of these particles. Furthermore, if you look at the rates are also sufficient in terms of the power injected per volume in the universe. And what actually ends up dominating the rates are events like 18HYZ. And you can see here, incidentally, that if 18HYZ were to be inferred as an on-axis rather than an off-axis event, then these volumetric energy injection rates would actually increase by up to 2 orders of magnitude. So taking it to be off-axis is conservative in that sense, and it looks quite promising as a source of ultra-high energy cosmic rays. So I will just leave the conclusions here, and happy to take any questions. Thank you.
Okay, questions? Brian.
Thanks, Paz. You may know the comment I'm going to make. So I agree with you that J1644, it's much more natural to invoke structure of the jet. Our interpretation was we were initially looking down the core, and then you start seeing the wings, and the wings have even more energy. But I wanted to ask you, because it seems to have been neglected by a lot of people modeling this, is in the first 10 days, there is a clear achromatic break. And we interpreted that as a transition in the hydrodynamics, because it's achromatic, as the reverse shock crosses through the ejecta and changes the pressure at the forward shock. So I guess my question for you is, do you think that these type of structures, we're used to in GRBs, where we should see a reverse shock phase that lasts roughly the jet duration, because in that case the jet was very active for a couple of weeks. Will that also apply to these off-axis cases? What is, in other words, what kind of, do we expect to see achromatic early breaks from the reverse shock?
Yeah, so I think certainly reverse shock on that time scale could operate. It could also be a deceleration peak that we see at that early time. And if you take a Lorentz factor for 1644 of order 5, you get the deceleration peak at the same time without changing any of the later time evolution. For the off-axis cases, you can also get reverse shock early on, but probably by the time that you observe those jets, if they're far off-axis, it's less important. So
we still need to be seeing some of the on-axis jet for 1644.
So for 1644, we need to be close enough that, yes, we're seeing something even early on, either from material that is only mildly away from the line of sight or material along the line of sight that is got slightly less energy, like in this picture that you were describing where you have a structure.
I think just as a general comment, I think this would make TD so interesting is it's like GRBs, we're always chasing the reverse shock because it's so short. TDs, we have
plenty of
2 weeks to see the same evolution unfold in that. So I think the early time radio data is really interesting for studying the shock hydrodynamics. Thank you.
Yeah, so you showed us double peak light curve.
Yeah.
Produced by off-axis jet, and could you give me some specific number when the time scale of the?
Yes, so there are 2 time scales here, 2 peaks. So the first peak is deceleration of material along the line of sight. These double peaked structures you only get if you have a structured jet. So the first peak is the deceleration time for material moving towards you, the observer. And the second peak is when the core of the jet is coming into your
I mean, some observationally, we have now 2 double-peaked radio light curves, and the first peak maybe happened about 100 days after the discovery, and now the second peak appears 500 or 600 days. So is it possible to produce this number?
It might be possible. I'm personally a bit skeptical that this specific explanation could be the most relevant one for TDEs because of this condition on gamma times theta c, but it might be possible, and it's worth looking into it. So maybe we can talk afterwards.
Can I say one more comment? I think if I remember correctly, to detect superluminal motion, the viewing angle should be slightly off axis.
Yes.
Right? So in this case, I guess maybe already the radio emission is very bright, so maybe we don't need any VLB observation, just very bright radioluminosity tells us this may be the jet. So
yes, but very bright radioluminosity, one can always argue if it's from one source or from another source. Superluminal motion will really be a clear-cut distinction between the options.
So this HYZ, let's say in the interpretation where it's off-axis, so one can compute this on-axis afterglow, right? Would it be crazy bright, like J1644? And then where are those?
Yeah, so it would be brighter, but take into account that by the time that we observe the peak, it's almost not relativistic. So, and that would also be true when you observe it on axis.
But you would have to extrapolate. We have not get the peak yet, right? So you have to wait until the peak shows up and then extrapolate backwards.
We're not quite at the peak, but
almost.
I would guess that we are close to the peak.
And then you have to extrapolate quite steeply upward, backwards if it were viewed on axis.
So there are 2 things that come into this. One is that by the time you reach the peak, you tend to be mildly relativistic, and this happens because you need to wait until new M crosses through the observed band. And this takes typically hundreds of days.
I'm wondering, where are those? Right, the other ones, let's say.
Right, we should check. But essentially, if you look at this rate that is inferred for things like 18 HYZ, although it's large because of the distance, it also means that the typical events are far away. And so it's a question of numbers, and it's a question of should we have seen even one of those events on axis, right? We saw one far off axis, so for every one, let's say for every 100 you see far off axis, you should see one on axis. So.
That's right. Thanks.
Yeah, I have a question about the ultra energy cosmic ray flux. Of course, I'm supportive of TDEs explaining everything, but I also been thinking about this in the context of neutrinos, and there it's very hard to think why TDEs dominate and not AGN, since there are more AGN, they're on for longer, and they can be just as powerful. So what's so special about these jets that they have to produce the cosmic ray flux? Why not just blazars or anything else?
Yeah, so I think it's the energetics which are key here in terms of getting this Hillas condition right, getting the acceleration time to be short compared to the escape time, even for the highest energy particles. And for the AGNs, there is a difficulty to explain the ultra high energy cosmic rays, because if you take a steady source, if you take some steady source that is the source of the cosmic rays that we see, then the inferred density of sources is too large, and that runs into contradictions with the fact that we don't see any asymmetry in the directions of the ultra high energy cosmic ray flux.
Fine, so but then you need a mechanism to suppress it still in AGN.
The theoretical reason might be that there's a working surface here where the AGN drills out and then there's no more shock. So I mean, I'm not saying this is the explanation. I just mean there's a difference between these jets and the AGN jets.
Yeah, and observationally we have this constraint on the plausibility of AGNs.
Thanks. Yeah, and one more fun fact is that if you have this dust echoes, then you have this very high density of infrared photons, and so from the delta resonance you could never get to these high energies, basically the same as the GCK cutoff with the CMB. But I guess you can have these jets always leading the echo because they escape relativistically, right? So you'd be safe from that.
Right. So that would limit the distance from which you can have contributions from them, and yes, maybe some would be able to escape that and still reach us on the leading edge.
Any last questions? Okay, let's thank Paz again.